Okay, this video is on small-scale behavior of polynomial functions. And we see here in example number 1, we've got 3 different polynomial functions, and they're all 4th degree polynomial functions. And as we mentioned in the last video, we know that in terms of large-scale behavior, since these are all 4th degree polynomial functions, we would expect that each one of these functions at large scale, that is, if we move very far back, have a really large viewing window to look at these, we'd expect each one of these functions, the graphs, to all look like the graph of their leading term. That is, they'd look something like this U shape, which is the graph of y equals x to the 4th power. Well, at small scale, that is when we look closer at, when we move in and look closer at the graph of a polynomial function, we see that they begin to look very, very different. So if we graph each one of these functions on our graphing calculator, we see that this one has this shape, this one has this shape, and this one has this shape. Now, one of the things that we're going to be looking at with regard to small-scale behavior of polynomial functions is where do these functions touch or cross the x-axis. And I can see for this function here, for f of x, this touches or crosses the x-axis in 1, 2, 3, 4 places. This one in 1, 2, 3 places, and this one in only 2 places. And these places here where the graph of a function touches or crosses the x-axis, these are what we call the zeros of a function. So let's take a look at the zeros of a polynomial function. So the zeros of a function are just the values of x that make y equals 0. That is, they're the values of x that make the function equal 0. That's why they're called the zeros of a function. Now, zeros are sometimes referred to as roots, sometimes referred to as solutions, and they're sometimes referred to as x-intercepts. All just different terms for the same thing. Now, the total number of zeros that a polynomial function has is always equal to the degree of the polynomial. And also, every zero of a polynomial function corresponds to a factor of that polynomial function. For example, if x equals 2 is a 0, then x minus 2 would be a factor. For example, if we had a function, a polynomial function, that we had written in factored form, like, say, like this. Now, this is actually a polynomial function, and I know it's a polynomial function because if I multiply these two binomials together using FOIL, then I'm going to get x squared plus 5x minus 14, which is a polynomial. Well, in factored form, this function looks like this. It has these two factors. One of my factors is x minus 2, and notice that if I plug in this value for x, if I let x equal 2, well, this factor becomes 2 minus 2, which is 0, which means that the value of the whole function becomes 0. That's what we mean when I say this value here, which is a 0 for the function, this value, x equals 2, corresponds to this factor of the function. And we're going to take a look at this some more as we go. Okay, so another thing, another characteristic of polynomial functions, another characteristic of their graphs, is something that we refer to as bumps or turns. A bump or a turn corresponds to a change in direction in the graph. Now, between any two zeros of a function, between any two 0 points on the graph of a polynomial function, there must be a bump or a turn, because in order for the function to go from one 0 to another 0, it has to cross the x-axis again, which means it has to change direction at least one time. Now, if we take a look at the shape of the graphs and the zeros and the bumps that we see for different typical polynomials. If I have a second degree polynomial, which is also called a quadratic, if I have a second degree polynomial, the shape, the typical shape of the graph of a quadratic looks something like that. It's got this characteristic U shape. Well, I can see that the number of zeros that I'm going to have for this particular graph, that's the places where it crosses the x-axis, I'm going to have 2 zeros. And the number of bumps that I'm going to have, the number of bumps or turns, is just 1. I've got a bump right here, or a turn, a change in direction right here. So I've got 2 zeros and 1 bump. If I have a third degree polynomial, also called a cubic polynomial, well, the typical shape of a third degree polynomial is going to look something like this. And notice I've got 1, 2, 3 places where this graph crosses the x-axis, which means I have 3 zeros. And the number of bumps I have for this graph is 1, 2. So I have 2 bumps, 3 zeros. A fourth degree polynomial, also sometimes called a quartic, well, the typical shape for its graph is going to be something like this. And notice now I have 1, 2, 3, 4 zeros for this fourth degree polynomial. And the number of bumps I have is 1, 2, 3. 3 bumps. So you can see that the number of zeros always corresponds to the degree of the polynomial. 2 zeros for second degree, 3 for third degree, 4 for fourth degree, and so on. And the number of bumps is always 1 less than the number of zeros. So number of bumps is always less than, I should say, is always 1 less than the number of zeros. Now, let's take a look at something that is referred to as multiple zeros. So take a look at these two functions here, f of x and g of x. Now, based on what we have looked at so far, since this function is a second degree function, then I would expect that this function would have 2 zeros, right? And since this function is a third degree polynomial function, I would expect that it would have 3 zeros. Well, if I actually take out my graphing calculator and I graph these two functions on my graphing calculator, these two functions are going to look something like this. In other words, for this function, I can see that it only touches the x-axis in just 1 point. And for this function, touches the x-axis here at x equals 4. For this function, this third degree function, I see it only touches the x-axis in 1 point. So I'm expecting to see it have 2 zeros. In other words, I'm expecting it to touch or cross the x-axis in 2 places. For this one, it only touches it in 1. Here I'm expecting it to touch the x-axis or cross in 3 places that it only touches in 1. Well, these two functions here show us examples of what we call multiple zeros. And in particular, this place right here is what's called a bounce. And this right here, notice that the graph looks flattened. These are characteristics of multiple zeros. For f of x, this point right here where x equals 4 is called a double root. And in particular, if a graph bounces off of the x-axis, you can see the graph kind of comes down here and it looks like it hits the graph and kind of bounces off. If a graph bounces off the x-axis, the 0 at that point will be repeated an even number of times. So, since this is a second degree polynomial, and I know it has to have two roots, this root right here is called a double root, which means that the roots for this particular polynomial are, we say the roots are x equals 4 and x equals 4, a double root. For this g of x function, x equals -1, where it crosses the x-axis, x equals -1 is what we call a triple root. And if a graph crosses the x-axis but looks flattened at that point where it crosses, then the 0 at that point is going to be repeated an odd number of times. So since this is a third degree polynomial, and I know I have to have 3 zeros for a third degree polynomial, this, where the graph is flattened, that tells me that this is going to be repeated an odd number of times, and that odd number of times is going to be 3 to match the degree of the polynomial. And we're going to take a look, we're going to talk some more about multiple zeros a little bit tomorrow in class.